Alright, I have a slope. Okay, so I have a slope. I have a brick, I guess. So I have a brick resting on the slope basically. And this time we can't neglect friction, right? Friction is important for the problem. Because we're trying to find, right? So what we're trying to find is that on a slope with some random angle theta and with a random brick on it with mass m, we're trying to find, I guess we're trying to derive an expression for what, like a general formula to find the minimum value for the static friction coefficient. So we're trying to find expression for this, general expression. So first things first, we should probably draw like a force diagram of all the forces acting on the brick. So let's see here. We know gravity is acting on the brick, right? I'm gonna break apart gravity like in a standard way. Like when we have a slope, we're gonna break into a force parallel to a slope and a force perpendicular to it, right? And this force is gonna have a magnitude mg sine theta, and this force is gonna have a value of mg cosine theta. Alright, so this is just a standard slope force, basically. Now, with static friction, right, this thing's not going to move at all. So there's going to be a force of friction right here, right? It's going to be a force of friction right here. That's going to be equivalent, like, to the magnitude of the force of gravity going down the slope. So I'm going to call this the force of friction. I'm going to get that the force of friction is equal to mg sine theta also. Right, it needs to perfectly counter the force of gravity going down the slope. So let's see here. We know the formula for mu static. Mu static is equal to the force of static friction, I should say. I should really change this to say force of static friction. Force of static friction. So we know the formula for, well, mu s, right, is force of static friction divided by normal force. Right? So what's our normal force? So we should probably figure out what our normal force is. We know the force of static friction. So normal force is basically, well, also mg cosine theta, because normal force goes like this, right? In the exact opposite direction to the perpendicular force. Like, the force of gravity that's perpendicular to the slope, the ramp, sorry. So yeah, that's basically it really. So we have mu static is going to be equal to the force static friction, so mg sine theta divided by the normal force, which is going to be mg cosine theta, right? And then, well, these will cancel out, and we'll get that mu static is equal to, well, just tan of theta, right? So mu static is equal to tan of theta, but here's the thing, mu static will be more than tan of theta also, because the force of static friction is kind of an inequality, really. Like, there's really only a maximum force of static friction, and force of static friction can just be anywhere below that maximum. But once it hits that maximum, the brick is gonna start moving. So we could say, actually, a better expression would be that mu static is greater than or equal to tan of theta, right? Tan of theta is just a minimum mu static. I mean, if there's more friction, this thing's still not gonna move, right? So that's basically our final expression. Mu static is greater than or equal to tan of theta. So not too bad, really. Really cool result. And stay tuned for more stuff like this.